A very good morning to all. Welcome to the lecture number 8 on complexity analysis of recursive algorithms. So in this particular lecture, we will see the definition of recursive algorithms and different types of recursive algorithms, and we would see some analysis, right? The complexity analysis of few of the recursive algorithms. So the definition of recursive algorithm, so it is a special case of one procedure calling another procedure is where the original procedure calls itself rather than some other procedure. So here the definition says that the original procedure calls itself rather than some other procedure. So a function calling itself again and again. Okay. So algorithms implemented in this way are said to be recursive algorithms. And there are different types of recursive algorithms. So there are total 4 I have classified here. So the first one is the linear recursion, and second one is the binary recursion. Third one is nonlinear recursion, and the final one, the fourth one, is mutual or indirect recursion. So we will see the definition of this recursion one by one, and then we would see some examples. So what is linear recursion? What is linear recursion here? So only one internal recursive call is made. Okay, only one internal recursive call is made within the body of the procedure. So right here, so for example, let us consider finding the factorial of a number. So here it is x factorial. So x factorial is usually, how do we write recursively? We write x factorial is equal to x into x minus 1 factorial, right? So here one procedure is calling, right? One internal recursive call is made within the body of the procedure here. So here x minus 1 is the other recursive call within the body. Now, so in general, what we can write is that if x equal to 0, then factorial is 1. So this is the terminating condition. Else factorial is equal to x into factorial of x minus 1. So this is the idea. Another example would be that we want to find the x power n. So x power n can be written as x into x power n minus 1. So here, in general, we can write if n equal to 0, then p is equal to 1, else p is equal to x into p of x comma n minus 1. So this is the recursive call, and this recursive call is linear recursion. And now let us take another very famous example of finding GCD of two numbers, right? We have been learning, we have been listening to this GCD since our school, our high school days, right? So here, GCD of two numbers, if it is given, how to find it, how to use algorithm to implement this, the procedure of GCD with two numbers. So greatest common divisor of A and B, where A is greater than B. So now let us take one very simple example of finding GCD of 22 and 8. Okay, so when two numbers are given, the first logic would be that I have to find the minimum of these two numbers, right? So that minimum of the two number in this case is 8. So 8 is placed in the first position, and then we take the bigger number and apply the mod with respect to the smaller number. So here GCD of 22, 8 is now split into GCD of 8, 22 mod 8, right? So now compute the answer for 22 mod 8. So the answer would be the 6, right? So which is equal to GCD of 8, 6. Now repeat the procedure again, same way. So GCD of 8, 6 would be GCD of the smallest number, right? That is the 6, then followed by the larger number, which is 8 mod 6 here. Again, you get the answer GCD of 6, 2. Again, you proceed because the terminating condition has not been reached. So again, you split this number. GCD of 6, 2 is again now GCD of 2, 6 mod 2. So in this case, you see GCD of 2, 0. So we reach the 0, and this 0 is the terminating condition here. Therefore, GCD of 22, 8 is 2. And GCD of, so in general, what we can write here is GCD of A, B is, okay, the body says if B equal to 0, right? When we get B equal to 0, then simply it is GCD is the small a, right? Means this a. Else GCD would be the recursive call. GCD is equal to GCD of B, A mod B, right? B, A mod B. That is the recursive procedure here. Now, another example would be the sequential search. The sequential search we have already seen, right? But not in a recursive way. So let us try to design, right, in a recursive fashion. Means finding the searching the element in a sequential manner. So here I write a function called as search of I, where I is the okay, the position, right? The position where which needs to be searched here, right? And so search of I, within that, if I is greater than n, then simply the element is not present, I can conclude. Else, if a of I, here it is small I, if a of small I is equal to key, then element is present. Okay, else if the element is not present, then what you do is that you search I plus 1. So now the search function, right, the search function is calling, okay, the subsequent index, right? It is calling again and again. So this is one example where you can convert any algorithm, right? Means the algorithm in a recursive. You can write the algorithm in a recursive way, but there are some drawbacks, right? You have to do a proper analysis before coming up with the recursive procedure, right? So you have to check the advantage with the normal function, normal logic, as well as the recursive logic. So we have to properly analyze that. So the number of times the recursion procedure is invoked is called depth of the recursion, right? The number of times you are calling the recursion is called the depth of the recursion. So now the second type of recursion here is the binary recursion. I think you are already familiar, right? The famous example of Fibonacci number, right? Fibonacci number is an example for binary recursion, where binary recursion is a special case of nonlinear recursion, right? It is a special case of nonlinear recursion. Two internal recursive calls are made here in this case, right? So example would be finding the Fibonacci number. So Fibonacci number, if I is less than 1, then f is equal to 1, right? Else f is equal to f of I minus 1 plus f of I minus 2, right? So the initial conditions are f of 0 is 1, f of 1 is 1. So this is this starting condition initialization, and then the algorithm would proceed like this. It would split f into f of I minus 1 plus f of I minus 2, right? And it adds the answer of f of. So in the recursion tree would look like this. So this is a pictorial representation of me splitting f into f of I minus 1 plus f of I minus 2. So here, for example, if you take Fibonacci number of Fibonacci of 4, if you take f of 4, so f of 4 will be recursively split into f of 3, right, and f of 2, right, f of 3 and f of 2. F of 3 is again split into f of 2 and f of 1. Again, f of 2 is split into f of 1 and f of 0. F of 0 and f of 1 is already known to us, so we get the answer, and then we get the answer of f of 2. Okay, and similarly, f of 3 is also right. We get the f of 3 answer, and then the answer goes to the f of 4. Similarly, f of 2, right, we have already split, and f of 2 is again split into f of 1 and f of 0. So recursively the answer comes in the bottom up fashion, right? Splitting is from top to bottom, whereas the merging, the answer comes from the bottom to the top fashion. So the what is the disadvantage? I think if you clearly observe this tree, right, this recursion tree, then you would see that there are many function calls which are unnecessary, right? So which are unnecessary. Now, for example, f of 3 here, f of 4 is split into f of 3 and f of 2, but you see that f of 2 is already f of 2, the answer is already available here. Now you see that when you split again f of 3, you again get f of 2 and f of 1. F of 2 1 already exists, and again you see in f of 2 you have already f of 1 here and f of 0. So f of 1 and f of 0 again they repeat in f of 2. So these are all some redundant calls. So you can also, while implementing this kind of algorithm, you can put some intelligence, because you already generated f of 2, f of 1, f of 0, right? You already know. So you can simply take that subtree, and then you can simply substitute that answer wherever there is, because your computation should be done only once, right? You should not be a what we call the repeated computation should be avoided. So that is the drawback here. And now the third type of recursion, that is the nonlinear recursion. So nonlinear recursion would come into picture when an algorithm uses a number of internal recursive calls within the body of the procedure. So one example would be the mutual recursion. So in this mutual recursion, the procedure A is calling the procedure B, and in turn procedure B is calling back the procedure A. So this is an example of a mutual recursion, and this is a case of nonlinear recursion. And now let us do some kind. Let us analyze the recursion tree, right? So we know that whenever there is a recursive problem, then it would generate the recursive tree. And now, what is the meaning of the recursive tree? Okay. So in the recursion tree, the width of the tree is proportional to the time. Okay, as the width of the tree increases and the time complexity increases. On the other hand, if the height of the tree, right, if the height of the tree increases, then the space complexity increases. So this is very, very important. This analysis is very, very important in case of recursion. So a recursion can be thought of as a sub-program being executed in a separate machine. So this may be the another way of interpreting a recursion. And when the other machine completes its work, it sends the answer back to the first machine, which continues its work. So once the execution is done, then answer is got back, and then the processing is done by the parent, right? And now, if a procedure makes two recursive calls to itself, then it will simply start two. It means that it will simply start two other processes working with the same instruction that it is using, right? So of course the data for the two processor would be different, right? It would be different data. When these two processes complete their job, they will send the answers back to the processor that turned them on, right? So this would so this is just like a parent-child relationship. Parent creates child, and then child gives back whatever the job which was assigned to the child, right? The parent has assigned the job to the child, so it returns back the answer, and then the parent would do further processing. So if they make in turn recursive calls, then they will simply set still more processes working. So once the child, right, if it makes another function call within itself, right, within its body, then it is simply creating much more processors, right? It's still creating more processors within that, and it would be time consuming. So now one example would be that machine one is right, this is a process 1, right? It is giving it has two children, machine 2 and machine 3, right? And now machine call, here you can see that this would be this one, machine 2 here, right, makes a call, right, 2, 4 and 5. So this you can see that, right, here 4 and 5 they are the children of 2, and 2 and 3 are the children of 1. So once they are ready with the answer, then they would give back to this machine 2, and machine 2 and machine 3 would give the answer back to machine 1. and machine 1 would give the final result. So single processor implementation. So single processor implementation is a non-recursive subprogram. In case of non-recursive subprogram call, what it would happen? There is a processor. Okay, there is a processor, and the processor calls a subprogram, and the subprogram. This is the subprogram. This is the processor. It calls a subprogram, and whatever the data is required has been given to the subprogram, and once the execution is over, then it gives back the answer to the processor. So in this case, it is a fixed storage area for a subprogram. So the drawback here is that the storage is fixed for the subprogram. So it has a limited capacity, so it has to work within that. On the other hand, the recursive calls, right? The recursive calls can make. So now in this case, the processor, the parent can make a call to its child, right? Child number 1, and now in turn the child 1 can call back, right, its own child, that is the child 2, and the child 2 will return back the answer to the child 1, means to its parent, and then child 1 will return the answer to its parent here. So in this case, the storage areas are created dynamically whenever a recursive call is made. So in this case, the memory allocation would happen in a dynamic fashion. So now we can see that this is a what you call recursive call tree. What we can say that initially the parent is parent is calling the function, means the procedure A, and A is returning back the answer, right? A is returning back the answer to yum, and yum is again calling back A for some work, and A is again returning back the answer. So this is what I'm trying to do is that I'm trying to trace the path of the execution for this recursive call. Now yum is again calling B. So B in turn, right, B cannot do the work, so it can what it does is that it has to do some more work. So B calls B again. So now you can see that the depth increases here. Again B calls itself. So B and once you can see here, once the B has this B, right, the third B here, it has executed, then it returns back the answer to the second B, and second B returns back the answer to the first B, and that in turn returns the answer to yum, right? So yum again calls C. When it calls the C, then it is the C is in turn calling D, and D is returning back the answer to C, and C is again calling E, E is again calling E, right? So this goes on, right? Here E gives back the answer to E, and then E returns the answer to C, and C will finally return the answer to yum. So this is what is what I can say, the path of the execution, right? The path of the execution here. So now let us see do some analysis with respect to this one, right? So we have the time, right? The time as x-axis, and we have the space on the y-axis. So now what we'll do is that we have the parent, right? Yum. So yum is calling A, right? Yum is calling A, procedure A, and A is returning back the answer. So now yum is calling again A, and yum is again, A is again returning back the answer, right? So now we can see that as we move on, there is a time, right? So that is why you see that the time increases as the number of processes, right? As the number of requests increases. So now here, third time the yum calls B, whereas here B is here, you can see that B is calling B again, and B is calling B again. So B will return the answer here, and then B is again returning back the answer to B, and B is returning back the answer to yum. And on the other hand, the yum will call C, C will call D, D will return back the answer, again C will call E, and E would again call E, right? Again E would return back the answer, and E would again return back the answer to C, and C would finally return the answer to yum, right? So now what you can see here, right? What is the observation here? So now the observation is that the time complexity of the recursion is proportional to the width of the tree, right? The time complexity of the recursive algorithm is proportional to the width of the tree, whereas the space complexity is proportional to the height of the tree, right? Space complexity is proportional to the height of the tree. So now let us do some kind of analysis here. Now, what would happen here, right? The space, let us take this y as space axis and this x as the time axis. So now what would happen is that m would call a, right? M would call a, and once the a returns back the space, right? Once the a returns back the answer, this a is freed up, right? The space is freed up. Again, m calls a, and a gives back the answer, and that space is freed off. Now m calls b, right? But the b in turn, we know that the b is calling b again. So the space is not free now, right? Because it requires some space. B is calling b again. So this is b is calling b again, right? So once this b returns the answer to this b, then this would be free here, right? This would be free here, and you can see that, right in the recursive fashion, this b would give answer to this b and it would return this. So now this space is being freed up now here. Similarly, next d is calling c is calling d, and d is again returning back the answer to c, and c is again calling to e is again calling f, right? E is calling e, and then again e gets back the answer, and then again e, finally you get the c, right? And c returns the answer to m. So this is what we can see, that the time and space complexity with respect to this example. So now let us take the example of 5 factorial. So in this case, 5 factorial is split into 4 factorial, right? Still we do not know the answer of 4 factorial, right? We do not know the answer of 4 factorial. So again, 4 factorial is split into 3 factorial. 3 factorial again it's split into 2 factorial. 2 factorial and split into 1 factorial. We know what is the answer of 1 factorial, right? Then again we start combining it in the reverse fashion. So 2 factorial, 3 factorial, answer is got, 4 factorial, and then finally 5 factorial. We get this answer. Okay, so on the other hand, if you see Fibonacci of 4, f of 4, so f of 4 is split into f of 3 and f of 2. F of 3 is split into f of 2 and f of 1. F of 2 is split into f of 1 and f of 0. This answer we know, then we can combine in the backward fashion, right? Here also f of 2 is split into f of 1 and f of 0. F of 1 and f of 0 is known, then I can calculate f of 2. So in this case, also you can see that first 4 will come, right? So 4, Fibonacci of 4 is Fibonacci of 3 and Fibonacci of 2, right? Fibonacci of 2 is again split into Fibonacci of 1, because Fibonacci of 1 is known to me. So I get the answer, and then you split, right? This would be f of 0. So once we get f of 1 and f of 0, then this will be calculated. F of 2 will be calculated. So now that space is freed off, and now again you see that f of 2 will return the answer and f of 1 will return the answer, and that would generate the answer for f of 3. And f of 3 is the, but still we have not obtained the answer for f of 4, because f of 4 was split into f of 3 and f of 2. F of 3 we have calculated, but f of 2 is remaining. So f of 2 again will be calculated, f of 2 and f of 1. F of 1 we get the answer, then we go for f of 0, and f of 0, when f of 0 and f of 1 is known, I calculate f of 2, and again you can see that f of 4 I can generate. Now if you clearly see that f of 2, right? So f of 2 is present here, right? F of 2, if you can see, right, f of 2, the answer of f of 2 is already there, right? Already here. So that can be used for, means that can be substituted in your program while implementing and reduce the time complexity, because f of 2 already you have calculated. So simply substitute the answer for f of 2 and you would get this. So you can see here, right? This part is already repeated here. So 2, 1, 0, 2. 2102. This part is already there. You already computed it, this one. Right? So you can simply substitute and save this particular time. Okay. So time calculations in case of multiple, right, x power n, right, in case of x power n, calculating x power n, if n equal to 0, then p is equal to 1, else p is equal to x into p of x comma n minus 1, which we have seen already. So in this case, let the time complexity function be t of n. So t of n is equal to 1 if n equal to 0, or else what you can do is that you have to split, right? You decrease the problem here into t of n minus 1. So t of n is equal to time taken to compute t of n minus 1, right? This is right, t of n minus 1 plus one operation for the multiplication, right? One operation for multiplication. So here now, so t of n is t of n minus 1 plus 1. So now if you try to recursively substitute here n minus 2, then you can see that this can be, right? So this is split into t of n minus 2 plus 2. Similarly, t of n minus 3 plus 3. Okay, so on t of n minus n plus n. And if you solve this recurrence relation, then you see that t of 0 plus n and t of n in this case is proportional to n plus 1, right? So it is t is proportional to n here. So time calculation in case of a Fibonacci number. So Fibonacci number is that if I is less than 1, then f is equal to 1, else f is equal to f of I minus 1 plus f of I minus 2. We have already f of 0 as 1, f of 1 as 1. This is the initial condition, right? So now in this case, what would happen? The time needed to for t of n, in this case, if n equal to 0 and n equal to 1 is 1, whereas if it is greater than 1, then it is t of n minus 1 plus t of n minus 2. This is right. This is the time required to get n minus 1. This is n minus 1 answers, and this is the time for getting n minus 2 answers here, plus 1 for addition, right? 1 for addition here. So now once we have this recurrence relation here, t of n minus 1, so if you simplify this one, right, you would get the so this would be in terms of if you see that, right, if you see textbooks or in the material, you would get the time complexity as O of 2 power n, right? So 2 power n, it is a factor, it is in terms of what we call the factorial terms, right? 2 power n. So here check how Fibonacci is inefficient on recursive implementation, so that you can answer this query here. Now, to get more ideas with respect to the recursive algorithms, you can refer R.G. Drome, chapter number 8. You can see that. Just see whether the chapter number is right, or because this is the old presentation, so maybe the chapter number is varying, right? So you can use recursive. You can learn more about the recursive algorithms there, and also you can use right. You can use the recursive algorithms for calculating the space complexity. So remember that space is more important in recursive implementations. Okay, because your algorithm may fail when there is some space constraint. So, so this is all for this lecture. Thank you.